Hello friends, with this video we are going to start our discussion on transistors. And to start with transistors, the first transistor that we will be seeing will be bipolar junction transistors, also known as BJT. Before we move into the details of BJT, we will just have a look back about what a transistor is. What is the elementary concepts behind the device called transistor?
Transistor, which is one of the very important device that makes use of semiconductors. Before we go into more details, we will see what is the basic objective of a transistor, or in what condition a device like transistor is being used. Consider 2 points, say A and B. When you connect a potential or a battery across these 2 points, there will be a current flowing in this direction. Due to the standard convention, the current flows from positive to negative. The current between these 2 points, say A and B, depends on the applied voltage. So as we increase the voltage, the current flowing through the connection A and B increases. Ohm's law, simple Ohm's law. But the basic objective of a transistor is that we need to make the current flowing between A and B independent of the voltage source that we are going to apply across A and B, which means even if we apply a 2 volt or a 5 volt or even 10 volt, the current flowing between A and B should be constant. Don't think that we can keep on increasing the voltage. There is a breakdown limit. Within the limit, whatever voltage we apply, we have a constant current across A and B. That is the basic objective of a transistor. Which means if we plot it graphically, if x-axis is VAB, the voltage across A and B, and the current IAB flowing through A and B should be a constant. This is one requirement. The second requirement is that we will have a third node, say C. We are having a third node C. By the application of voltage or injection of current, any of the one mode, onto this third node, we could control the current between A and B. Which means if the applied voltage at the third node is increased to 5 volt, the current flowing between A and B should increase. If it is increased to 7 volt, still the current increases. Or So for 5 volt we are having an increased current 7 volt. Initially it was 2 volt. If the voltage across or voltage applied at the third node is decreased, say 0.5 volt, 0.5 volt, the current decreases. At 0 voltage, the current goes to 0. That is true for every applied voltage. But in a position in this area, the current flowing between A and B does not depend on the voltage applied across A and B, but it is being controlled by the voltage applied or the current injected at the third node C. This type of action is the basic objective of a transistor. 2 points to remember. The current across A and B remains constant for any voltage applied across A and B, but it can be varied in two methods. One is applying a voltage at C. We'll see what are the differences. Applying a voltage at C or injecting current at C. With this action, transistor can act as a switch, which is the primary application of a transistor. By applying the sufficient voltage, you could control the current through A and B from on position to off position. The simple functionality of a switch is that it allows current or it doesn't allow current. That is one application of transistor. Another application of transistor is it is used in logic devices or processing devices, universal gates, etc. Transistor is also used as memory device. It can be also used, or it is used in amplifiers. Above all, we see transistors in every another electronic device, carrying out various functionality in the electronic circuit. So, like the PN junction, which was the basic device using semiconductor, transistor is a device which has multiple application in various devices using semiconductors. Now we will see a general classification of transistor. We can classify transistors. There are different types of transistors. We can classify them into two groups in a general thought process. How it is being grouped can be explained by an analogy. Consider a pipe carrying water. A pipe carrying water. So the transistor is like a pipe carrying water, and the flow of water in the pipe can be controlled either by having a tap in between. As we tighten the tap, the flow of current decreases, or the water flow decreases. We could even, at a point, we could even close it completely so that no current flows. That is also possible. Pinching off of the current is possible. Or we could adjust the position of the tap and control the flow in the pipe. Another mechanism is that we could change the shape of the pipe. Change the shape of the pipe by applying an external force so that the pipe elevation changes. This will also affect the flow of water in the pipe. This will also affect flow of water in the pipe. Likewise, we are having two mechanisms of controlling current in a transistor. This type of transistor where we apply tap is similar to applying of a field, where voltage is applied in the third node, the node C. This is the C node. This is A and this is B. The examples of such type of transistors are field effect transistors, FET. The other examples are MOSFET, MESFET, MISFET, so on and so forth. In the second category, the change in elevation, this change in elevation is brought about by injecting current. Here, what we do is we are applying a field or we are applying a voltage. Here we can change the elevation using injection of current into the third node C. We are having other two nodes A and B. This type of transistor, the examples of this type of transistors are BJT, which is the bipolar junction transistor. We are having other examples as HET, HBT, so on and so forth. We will be concentrating on, or we will be starting our discussion on transistors with deeply analyzing the BJT first. Why? Because it is more closer to the discussion that we had during our discussion on PN junction. So that's why we will be starting our discussion on different transistors. We will be seeing MOSFET in our coming modules, but we will start our discussion on transistors by analyzing the bipolar junction transistor. See what BJT is in detail. As I had mentioned earlier, BJT stands for bipolar junction transistor. It is made of two PN junction put back to back. so that we have 3 nodes or 3 node system that we discussed earlier. Consider a PN junction, NP junction, and another PN junction, PN junction. When combined together, we will get a transistor which is an NPN transistor. NPN transistor. There is another type of transistor which is known as the PNP transistor, where you have P, N, P. This part, the one part of the transistor is known as the emitter. This part is known as the collector, and we have base here. As a PNP or NPN transistor is normally used for amplification, the basic requirement is to have the emitter base junction forward biased. Which is this junction is forward biased, and this junction, which is the collector base junction, will be reverse biased. This is the requirement for transistor to act as an amplifier. If we draw the band diagram of an NPN transistor or a transistor, we will be discussing the transistor using the NPN type of transistor. So the transistor will be NPN transistor block diagram will be like this. NPN. If we draw the band diagram of this NPN transistor, remember the band diagram of the PN junction. The Fermi level at equilibrium will be constant. This is the Fermi level. And the band diagram will look like the NP side will be like this, and the PN junction will be, band diagram will be like this. So this forms the band diagram of an NPN transistor. Now, in order to make this transistor work as amplifier, this junction has to be forward biased and this junction will be reverse biased. As you know from our previous discussion on PN junction, on reverse biasing, the depletion region or the potential barrier increases, so that on applying biasing, here what happens is the potential barrier increases here so that it comes down a bit more, so that this potential barrier is increasing. Let us see how the transistor works when the emitter base junction is forward bias and collector base junction is reverse bias. I am just redrawing the energy band diagram without drawing the Fermi level, so that on application of reverse bias we have more potential barrier at the reverse bias junction, which is the collector base junction. As you all know, the emitter base junction is forward bias, so that a negative potential is applied at the N side, so that electrons from the emitter side moves to the base side. This is in the energy band diagram, this is the emitter, base and collector sides. The electrons reaching the base will recombine with holes here, and whatever electron is remaining on reaching the collector base junction, which is reverse biased, gets swept to the collector. If all the electrons coming from the emitter is recombined in the base, there won't be any current to the collector side. So the design will be made such a way that only part of the electrons coming to the base is recombined. We apply or we inject a base current to maintain the required objective, which is the current flowing from emitter to the collector does not depend on the potential applied between the emitter and collector, but depends on the injected current to the base. If you remember our previous discussion of 2 points A and B, the potential connected between them does not control the current, but the the current injected at the third node, which is the base, controls the current between A and B, which is the emitter and collector in this case. This is a basic elementary explanation of the working of a normal transistor.